in Southern California, not far from Jet Propulsion Laboratory, and her grandmother worked on the Apollo moon missions, so she was exposed to space exploration from a very young age. She graduated with a bachelor's degree in astrophysics and mathematics in 2002 from the University of Oklahoma, then attended graduate school in planetary science at Cornell from 2002 to 2006. During this time, she worked on the science team and mission critical operations team for the Mars Exploration Rover missions, Spirit and Opportunity. Later, she taught high school math and physics for 10 years before becoming a manager for the Spacecraft Planetary Imaging Facility, or SPIF, this July. She lives in Lansing with her husband and their 2 daughters, Toki and Sonia. Toki, her oldest, is named after the Opportunity rover. It is Japanese for time of opportunity. Sonia, which means wisdom, is in honor of her grandmother's Scandinavian ancestry and her work on the lunar rover. Please join me in welcoming Ms. Zoe Learner Ponterio.
Thank you very much, Nicole. That was a wonderful introduction. So, as you've heard from my history, I usually don't get such a wonderful introduction. I have been both a scientist and an educator. And now in the job that I have, I love because I get to do both. I get to both do some research support, and I get to come out and do this and do education. So this is really living the dream for me. And as she said, I have worked on a mission to Mars, and so I have an insider's view of this, and I would love to build on the reference to the because they are hard. That's a wonderful way to lead into this. Okay, so if you want to click down. All right, so we've got our solar system. And I'm going to be taking you on a pretty quick tour of it. A lot of times I go into a little more depth, but I want to make sure that we have time at the end for some discussion. And we're going to gradually work our way from the inside on out. And we're going to be telling this story not as a series of facts and figures, but as a story of exploration, because it's called the Spacecraft Tour of the Solar System, not the Wikipedia tour of the solar system. So the first planet on our journey is Mercury, and the first spacecraft to visit Mercury was Mariner 10, and we sent it, and we can, there we go, there it is, first pictures of Mercury's surface. Unfortunately, we didn't get all of it. Challenge number 1 of exploring space is you are about to do something that no one has ever done before, and you're going to go somewhere that no one has ever been before. If you're a scientist, this is exactly where you want to go, where you don't know stuff. But if you're an engineer, you want to know exactly what it's like where you're going so you can design the best spacecraft for the job. But the scientists say, well, I don't know. That's why we're going in the first place. And they go back and forth, and ultimately they take their best guess. Mariner 10 didn't go into orbit around Mercury. It passed by Mercury 3 times. They figured each time they'd see half the planet, and between 3 passes, get all of it. But that didn't happen. They saw the same half of the planet all 3 times because they didn't know about Mercury's spin rate. It's in resonance with the sun and its orbits, 3 rotations for every 2 orbits around the sun. This is why you don't see us ever go someplace and then just check it off the list and never go back. We don't do that. Because every time we go, we do get answers, but we end up with more questions. We end up realizing, oh, now we know how to better design the next spacecraft. We're always thinking about the next spacecraft we're going to send there. So we went back to Mercury, of course, with Messenger in 2011, and we went into orbit around Mercury this time, and we got the planet in full color. So technology also gets better. So down arrow, this is a typical Mariner 10 close-up image of the surface of Mercury, but down arrow, that's a Messenger image. So you definitely also go back after a decade or so because you have so much better technology, better cameras, better instruments, and you can answer even more questions. And next. You stare at a lot of images as a planetary scientist, I must admit, and if you stare at things long enough, just like looking at clouds, you start to see things in the image, and I'm wondering if anyone sees it yet, but next arrow. Yep, there it is. now you can't unsee it, right? Now it's just there, burned in your memory. That's the Cookie Monster crater, forever. All right, the next planet on our journey is Venus. And when you first look at Venus, this is all you see. Venus is about the same size as the Earth, and it's made of the same stuff as the Earth. It's a rocky planet with a metal core. And yet when we look at Venus, it looks completely different. We can't see the ground. Venus is covered in this huge blanket of thick atmosphere, 100 times thicker than Earth's atmosphere. And those yellow clouds are made of sulfuric acid. That atmosphere made of carbon dioxide being so thick is like a big puffy jacket. It's a greenhouse gas, and it's a greenhouse effect gone out of control. So even though it's not the closest, it is the hottest, clocking in at 860 degrees Fahrenheit on the surface everywhere all the time. The atmosphere spreads that out completely. That's hot enough to melt lead. And that thick atmosphere creates an atmospheric pressure at the surface that would crush you like you were at the bottom of Earth's oceans. So this is not a very nice place to go if you're used to life on Earth. However, Venus is often considered Earth's sister planet because of the similarity we would expect to see in the geology, because the planets are structured about the same. Now, there's two ways to go about handling clouds. One is to send back a spacecraft, which we did with Magellan, that has radar. Radar can see through clouds. So now we have a radar image of the surface of Venus. And this is not what it would look like to your eyes. You can't see in radar. So even though this is not what it would look like to you, this is still a fascinating way to look at the surface of the planet. The orange color is fake. People ask, oh, it's the orange. Well, it's radar. It's not orange. It's radar. We put the orange in because despite all the fancy computers and instruments we have, the majority of the science happens still with the human brain, which is connected to human eyes. And human eyes are color vision. And it's been shown that if you add false colors, that the human eye can pick out details better. So false color is a big tool that we use in science imaging. So there's Venus in topography, blue, low elevation, red and white, high elevation. So once we take away the atmosphere and we forget about the surface being so horribly inhospitable, again, a bit of a sister planet. However, strangely, we don't see as much similarity as you might expect. Venus does not have plate tectonics on it like the Earth does, but it does show signs of tectonic stress. So this creates a great way for us to try and understand the Earth better by looking at a planet that seems to be geologically structured the same but still has significant differences on it. And one of the most common questions I get is, who cares? Why are we going out and looking at these other planets? We live on Earth, why aren't we focusing on Earth and studying Earth? The point here is that we will never fully understand the Earth as a planet if that's the only planet we ever look at. It'd be like trying to understand mammals by only looking at dogs. It's just not going to happen. We need context. We need to look at things outside of the range of Earth and compare them. So comparative geology, comparative meteorology. We will understand the Earth better by exploring these other planets. So that is a big push. If you really are only interested in bringing it back to Earth, there's your reason, right there. For me, it's reason enough to say because it's cool and humans are natural explorers, so of course we're going to go out there. But it does benefit us directly back here on Earth. The other solution to seeing through clouds, of course, is to land on a planet. So next one. Bye, Cookie Monster. All right, so the Soviet Union did manage to do this twice with the Venera 13 and 14 landers. And they each lasted about an hour before they were, I don't know, crushed, melted, dissolved, vaporized, take your pick. Something happened and they stopped working. But before they did, they sent back information from the surface to confirm all of these things we suspected. The rocks, very basalt, very lava rocks. They're all volcanoes on Venus that we believe are currently active. And so this shows the many approaches you can take to exploring a new world. Now that brings us to the Earth and then out to Mars. I don't spend a lot of time talking about Earth, and that's because our department is about planetary exploration, And Cornell has an Earth and Atmospheric Science department in another building, so we tend to stick to the other planets, but as I said, we always are looking comparatively back to the Earth because that's what we know best. Now, one thing that is also important about going back, especially if you're looking at landing somewhere, if you just land once, you can't just say, okay, I know what it looks like now. I landed once, I looked around, got it. Because imagine that aliens send a probe to Earth, and that probe lands somewhere on Earth randomly. The Earth is 3/4 covered in water, which means if aliens took that approach, they would conclude that the Earth looks like that. Which, of course, some of the Earth looks like that, but certainly not all of the Earth. So that's another reason to keep going back, because these planets are each their own worlds, and we need to land more than once in different places to truly understand what the planet is like. Now, we mentioned Apollo, so I'll throw in the moon right there. And yes, my grandmother got to be a part of that. She actually worked on the Lunar Rover navigation system, and then I went on to work on a Mars rover, so we're thinking this is just a family business here, that we send rovers to other planets. Her signature is on the Lunar Rover, which stays on the moon. My name is signatured on the Mars rover on Mars. So I'm not sure many people can claim that their family has two names on two different celestial bodies. Who knows what my kids and grandkids are going to do. Now, Mars is probably the planet we know best besides Earth. Now, it is smaller than Earth, but it's still a big whole world. It's not a teeny tiny world. And for those of you who are in high school geometry should know this, that if Mars is half the diameter of Earth, then can anyone tell me what the surface area is compared to Earth? Who knows their scaling rules? I hear whisperings of it. Area is length squared. So a half squared is? A quarter. Very good. So a good way to think of how big Mars is that the total surface area of Mars is about the total land surface area on Earth. It's still a big place. Now, it does have some very Earth-like features, like a North Pole. So everyone can see that. There's a North Pole. There's also a South Pole. So those poles do contain water ice, about 1 to 3 kilometers thick of water ice cap there. We've long known there is water on Mars. The interesting thing that we were looking for as far as water on Mars was there ever surface stable liquid water? In other words, were there ever lakes, oceans, rivers, and things like that? Things we don't see on Mars today. There is water on Mars, it's just not on the surface and it's not liquid. Now, despite being smaller, Mars does boast some impressively huge features, which you can see as we move around here. Maybe I'll pause this for a second and bring us around to there. I think that's about right. So here, across here, we see a huge crack. If you go to the next slide. That crack, if I showed you here, you wouldn't know how big that was. That's one of the nice things about the magic planet, is by looking at the magic planet, we can actually see how big this thing is on the whole planet. Imagine something that size on Earth. Maybe the Andes mountain range might come close to it. So next slide. There's a comparison. It would stretch across the entire United States. Our Grand Canyon is only like that big. So this is a thing that was caused by upwelling inside the planet. There was pressure that pushed the crust up and split it open. Now that pressure also created another feature, the Tharsis region. So that's right over here where there's very smooth and lots of volcanoes. Next slide. The largest of these volcanoes, Olympus Mons, is the largest volcano in the solar system. And again, it's this big on the whole planet. So for comparison, it's the size of the state of Arizona. Now, Mars's atmosphere is very thin. It's 100 times thinner than Earth's atmosphere, and this is 3 times the height of Everest at the summit. That means that if you got to the top, you'd practically be in space. You'd be above almost the whole atmosphere. But it's so wide that you would walk all around this and not even realize you were on a mountain. It would seem flat to you. You could hike from the base to the summit. You would have gone up 3 Everest worth and never noticed you were walking uphill. So Mars does have some very impressive features to it. Next. Now we've landed several times on Mars. As I said, you never go once. This was our first landing, Viking 1. Next. Viking 2 landed pretty far north. In fact, we can take a look here. Here we go. So this shows topography and the different landing sites are marked. Viking 2 landed way up here to the north. That is frost. That's some early morning frost on Mars. Next. In 1997, when I had just graduated high school, Pathfinder landed. And Pathfinder was a lander, sat there, but it did carry an important passenger. Next. This little girl here. That's the Sojourner Rover, and that was the first time we had a non-manned roving vehicle on another planet, right? We had the Lunar Rover, but somebody had to drive it. Now, the challenge when you go out this far, beyond the moon, is that you can't drive this thing in real time. It takes 4 to 12 minutes for a radio signal to get from Earth to Mars, and then another 4 to 12 minutes for it to get back. By the time you saw something to avoid, it would be too late. So we needed something that could drive itself. We needed something that we could send up a bunch of instructions to, and it would do it all by itself. And it worked. It worked beautifully, and that ushered in the era of the Mars rover instead of the Mars lander. And I got to work on the Mars exploration rovers, Spirit and Opportunity, over on the left there. We built 2 of them. And then Curiosity. And the next Mars rover, which will be launching in 2020, will also be big like that. This is about this high. Curiosity is about this high. So now we're roving on Mars. We still can't go very far as the whole planet's concerned, but at least we can roam around and explore different areas. So there I was back at Jet Propulsion Laboratory on January 4th, 2004, waiting for Spirit to land. Spirit was going to land first. And she landed, and the first images came down, and the room erupted. We were among the first people to see it. We were so excited it succeeded because it's hard. And we were very nervous because we had just come through 2 failed Mars missions in a row before this. We were so nervous, and we were just hoping against hope, please let this work. We poured everything into this, and it worked. And as exciting as that moment was, I have to admit, begrudgingly, to a tiny bit of disappointment, because it kind of looks like every other picture from a Mars lander I've ever seen. It's red and rocky. Okay, so does all of Mars basically look red and rocky? Yeah. So the problem with rocky, loose rocks and dust is that you're not looking at the rock where it formed. You have no context for that rock. And that's all we had ever seen on Mars. Loose rocks, dust, what we call regolith in geology. And then 3 weeks later, Opportunity rover landed. And once again, we're back in the room. And once again, we're holding our breath to wait and see if it survives landing. And then the first image came up from that one. And it's a moment that I will never forget because the whole room went dead silent. Because what they saw was so strange that for a second or 2, we thought there must be a malfunction. That doesn't look red and rocky at all. It's a little red, but in the beginning we just saw a bright band and a dark band and a bright band and a dark band, and we were like, oh no, something's gone wrong. And then the images came down, some better resolution, some color came down, and the room exploded. Because we realized what we were seeing was something no human had ever seen before. The surface of Mars. Right there. That's an outcrop. We landed in a little crater where nature had done the excavation for us. And for the first time, we got to look at bedrock. We got to look at rocks where they formed. And in that outcrop was the first time we found convincing physical evidence for liquid water on Mars, because the layers we found in that outcrop were rippled. They showed that those were sediments that had been laid down in a lake or a sea about 3.5 billion years ago. As we continue to explore with opportunity and spirit, they have found overwhelming both physical and chemical evidence that Mars was indeed once wetter and warmer. Even at that peak time, it still would have been a dry, cold version of Earth, but certainly hosted lakes, oceans, and possibly life. Now, we only thought Spirit and Opportunity would last about 3 months. That was our hope, a minimum of 3 months. Mars weather, normally pretty calm, nice thin air, just a few clouds, but every once in a while this happens. Big global dust storm. And if you are solar powered like Spirit and Opportunity, that's bad news. Next. Not only does it get dark, but then even once the dust clears, next, your nice, clean, shiny solar panels aren't so clean and shiny anymore. And we were getting towards the end, and we were thinking, okay, we're getting down in power, this is probably close to it, and then we came in one day and the engineer said, you're not going to believe this. And we said, hey, we're scientists, we see weird stuff all the time, try me. And they said, you're back up to full power, up, no, up, sorry. They were clean again. And we said, we're right, we don't believe you. What just happened? So we had to look around, we had to work an issue that we had no idea how to explain. So now next, and they kept on getting dirty and clean and dirty and clean. So next, we looked around. We saw some weird features. Watch this guy. Next. It moves. Something tall and skinny, casting a long, skinny shadow. We'd seen this on Earth. Next. Dust devils. Dust devils like we have here in the deserts on Earth. Next. And there they are on Mars. This is not CG. This is a real movie of dust devils on Mars. So what we discovered was the dust devils are friendly little solar panel vacuum cleaners. We never thought that would happen. Things you don't anticipate. The engineers didn't know it was going to happen. We didn't know it was going to happen. But this is one of the reasons that these rovers that were hoped to last 3 months lasted Spirit 6 years. Opportunity, my dear daughter's namesake, is still going 14 years later. Still run most days from right above my head, 1 floor up from me. I pop up and say hi every once in a while. We did not think we'd be getting ourselves into such a long-term commitment, let me tell you. But there it was. So this is, again, the unexpected happens. And you don't know until you go there. So next. We also landed near the pole with Phoenix. Yes, lander. Well, at the pole there's not a lot of solar energy, so not enough to drive. But those are water ice patches exposed at the surface there. And when we thrust it down, we melted it. And so if you look closely, there's some spots. Right there, there's a spot. That's a water droplet from splashing up from the landing on those ice patches. Next. And here is the Curiosity rover, nuclear powered, because we thought solar power was going to be limiting. So we designed a nuclear powered rover. That's before we knew that they were going to last for years. Who knew? All right, now we know. It's still better because at least when you're nuclear powered, you can do operations at night. So there is that advantage to it still. Curiosity was hoped to last 2 years. She's coming up on 6 years, still going. Next. And this is where she's hanging out. She's in a giant crater that has a central mountain peak, and she is climbing through the foothills of that mountain. And all of those layers are a geologist's dream come true, because those are like the pages of a book. You can read those layers and read the geologic history back in time. And at the bottom of those valleys are filled with clays. All sorts of different clays that say, yes, this was a crater lake at some point in the past. Next. Mars does have 2 moons, but they're much, much smaller than our moon. In fact, its biggest one, Phobos, over here, only about 20 miles across. They look more like asteroids, and this is an asteroid up there. This is the other moon, Deimos. So, from Mars, next, we do take a quick stop at the asteroid belt. We have explored several asteroids, including the largest asteroid in the main belt between Mars and Jupiter, Ceres. Ceres, next. It's not small. It's the size of Texas, and it's round, and some argued it should be a planet. Others said no, because it's in an asteroid belt. And that debate went on for a while, and we'll come back to it again, because it didn't end. It's still going on. All right, next. Oh, there's Houston. All right. You missed a bunch of Houston. All right, so there's a nice close-up of Ceres. Guess what we found about asteroids is that they're packed full of more than just rock. They have a lot of water, ice, and organics and salts in them, too. So keep that in mind. All right, then we have the king of the planets, Jupiter. And Jupiter has its great red spot, which is about 3 times the width of Earth. So that's impressive. This is from the Galileo spacecraft, which was there in the 90s. But now we've got another spacecraft there named Juno. And Juno has been sent there specifically to study the clouds of Jupiter. So as beautiful as these Galileo images and the Voyager images are, now that we have Juno, we get these. And if you ever need a moment of zen, I urge you to go to Google Images and type in Juno spacecraft or Juno Jupiter and just enjoy. Just enjoy, because they're gorgeous. Juno is special in that it went into a polar orbit, and so we saw the poles of Jupiter for the very first time and saw that they are bluer than the rest of the planet. Now, Jupiter does boast almost 70 moons, but 4 of them are much larger than the rest of them, and in fact, 3 of those are bigger than our moon. And one thing you'll notice about them is you say moon, you think our moon, and a lot of people just think all moons look like that, but it's not true. You can easily see from this picture, each moon is its own little world. We're first going to look at this one, Io, and Io has volcanoes. Lots and lots of volcanoes, and they're always going off. So next. There's one exploding. An erupting volcano. And Juno actually took a little break just a few weeks ago from looking at Jupiter's clouds to turn and take a little snapshot of Io to see what's going on there. Every single one of those dots is a volcano erupting. So Io is a very interesting world, and now we're going to jump to the other extreme, the smallest one, Europa. Looks quite different. Europa is covered in ice. Its entire crust is made of water ice, with many cracks running through it. And underneath that ice is an ocean, a vast ocean of salt water. Next. More water than Earth has in all of its oceans combined. This is currently one of the places we think could have life now. Mars, we're mostly thinking past life. There could be life in that ocean right now. There's a mission that's being developed, and it's called the Europa Clipper, and it's going to go back specifically to Europa to investigate that. We come now to Saturn, beautiful Saturn, which unfortunately the magic planet can't do it true justice because I don't have the rings, right? And what's Saturn without its rings? Turns out it's still Saturn, because one thing we recently found with the Cassini spacecraft that just finished 13 years at Saturn is that those rings have not always been there. The rings are relatively new. We're just lucky enough to be alive right now at a time where Saturn has big, glorious rings. But we think now that it goes through cycles of having rings and not having rings, and that the other planets in the outer solar system also go through those cycles. So rings are dynamic. They don't always just stay there the way they are. At the North Pole of Saturn is a very curious feature. Unlike all the other circular bands of clouds, the North Pole has surrounding it a hexagon. An almost perfect, stable hexagon that's been there as long as we've been looking at the planet. And if you ask me why is it there, I'd say, I'm not sure, but I listen in on the scientists talking about it every Tuesday. They're working on it, and at the center of that hexagon, there is a massive polar vortex with 1,000-mile-an-hour winds. Jupiter didn't have this, right? Jupiter's pole was just a bunch of little storms. Saturn is one big storm, and there's one at the South Pole too, but no hexagon. I don't know. Next one. Saturn's clouds sometimes don't get as much credit as Jupiter's because when you look at it like the magic planet with our eyes, they all look kind of brownish. But if you add false color, I say Saturn's clouds are just as glorious as Jupiter's clouds. They just need a little oomph. The colors are about chemistry, temperature, and pressure, and all those different conditions. Next. Saturn does boast some storms. There is a huge storm that builds up every 30 years or so on Saturn. That storm on the planet is about this big. And it actually travels and trails all the way around the planet and comes back to its own tail and then dissipates. And, oh, that's a strike of lightning right there, that blue spot. So they're kind of like big thunderstorms. Okay. So the rings in Saturn, they're big, all right? But the rings actually go out farther than that. The next one. That brings us to one of our favorite Cassini spacecraft images that was taken, which was to send Cassini behind the night side of Saturn. Use Saturn to block the sun so that we could let the sunlight come through the rings and see the structure in them. And I do hope all of you were smiling that day because, know it or not, you had your picture taken by Cassini. So here's your moment of perspective. That little blue dot, that's it. That's all of us, everything. That's the whole shebang right there. All right, now that outer fuzzy ring, what's up with the fuzzy ring? When the rings are all nice and even, but not that one. That's because that ring is being made right now by a very surprising little moon. The little moon Enceladus. Saturn's moons are mostly made of water ice. Enceladus was one of many known icy moons of Saturn. It's small, it's much smaller than Europa. It's about the size of Scotland. It's not very big. But when we got there with Cassini, we saw something very strange happening with Enceladus, and that's that it's shooting stuff out of its south pole. Next. At the South Pole, there are these huge cracks. And yes, south is at the top of this image. We're in space. There is no up or down. Who says south is down? South can be up. Who cares? So there's these huge cracks, and stuff is shooting out of those cracks. So we said to Cassini, hey, Cassini, go fly through that stuff, those plumes. Tell us what it is. And Cassini came back with the results. Despite being tiny, Enceladus also hosts an ocean. And it's an ocean with about the same salinity as Earth's ocean, same saltiness. There are simple organic compounds in it. And there's silicates indicating that there's hydrothermal activity on a rocky ocean bottom. Everything we know about this ocean says it's exactly like the environment we found here on Earth at the bottom of the ocean and the white smokers, where there's life teeming all over the place, tube worms, crabs, everything going on. So now we know yet another place where we could have current life happening. And so obviously we're already thinking of going back to Enceladus because Cassini's instrument was not designed to look for life. Nobody thought we'd be looking for life at Saturn. That's way out there. Too cold, right? Turns out not. So now we want to send another instrument back because Cassini could not tell us whether or not there were things like amino acids or fatty acids or DNA.